In this video, we're going to look at the final examples coming from section 3.2 on the fundamental theorem of calculus. So these questions, it says evaluate each indefinite integral. So before we were using language of finding the antiderivative of these functions, but another way of saying that is to find the indefinite integrals over these functions. So let's take a look at number 12 first. So what we just saw in the previous example was a method for finding the antiderivative of power functions. So recall the integral of x to the n dx is equal to x to the n plus 1 over n plus 1. And then, of course, we want to add a c to make sure we indicate that our antiderivative could have any other constant being added to it, and the derivative of that function will still be what we want. So again, that's writing our antiderivative as that family of functions. So let's take a look here. So similar to differentiation, integration over a sum can be split up amongst each term in the sum. So if we want to find the antiderivative of this entire sum, it's enough to find the antiderivative of each term and then add those antiderivatives together. So let's go ahead and do that together in number 12. So here we want to find the antiderivative of negative 12 x to the fifth. So if I just had x to the n, the antiderivative would be x to the n plus 1 over n plus 1. So here I have a 5 instead of n, and I'm just multiplying by a negative 12. So multiplying by a constant doesn't change the antiderivative at all. We just have a negative 12 that we're multiplying that function by. So for example, in this case, the antiderivative of this first term would be x to the 5 plus 1 over 5 plus 1, all times negative 12. So we see that we're just using that rule that we just found and then multiply by negative 12. So multiplying by a constant just multiplies our antiderivative by a constant. And so now we could say plus c here, but then we still have another term to anti-differentiate. So for this term, again, we'd use the power rule. We still have that 3 that we're multiplying by. And we have x to the 3 over 3. Recall, in this case, our power is 2, so we add 1 to the power and divide by the power plus 1. Now again, we want the plus c, and let's just clean this up a little bit for our final answer. So a couple things. Well, first of all, I can just do that addition and simplify. So I get negative 12 x to the 6 over 6 plus c plus 3 x over 3 cubed plus c. So notice I should have different c's here because I might have different constants, or these constants are coming from different places. So I'll call it c twiddle. But it doesn't really matter in the end. If I'm adding two constants together, in the end, their sum makes some other constant. So I don't have to include both of these c's here. So in cleaning up a step further, let's go ahead and simplify and clean up both of those plus c's. So now I have negative 12 over 6. So I can simplify that to be negative 2 x to the 6 plus my 3 cancels my 3 here. So plus x cubed, all plus c. So is there any other simplifying I can do? Nope. So our final answer is negative 2x to the 6 plus x cubed plus c. And then how would you check that? Well, we find the derivative of this function and confirm that the derivative is our function here in the integral. So I encourage you to go ahead and pause the video and check that on your own to help deepen your understanding of finding antiderivatives. Awesome. All right, and when you're ready, let's take a look at number 13. So number 13 is very similar to number 12 that we just did. So now we have 3 terms. So what I'd like you to do is pause the video and find that antiderivative on your own. And when you're ready, we'll check answers. So taking the antiderivative of each term should look like the following. 10 x to the 2 over 2 plus 6 x to the negative 2 over negative 2 minus 3 x to the negative 3 over negative 3 plus c. So just keep in mind, if we have a negative exponent, when we take that antiderivative, we're going to add 1 to that exponent and then divide by the exponent plus 1. So in this case, if our exponent is negative 3, add 1 gives us negative 2. So then we have negative 2 both in the exponent and in the denominator. And similar story here. So if you got a different answer, at this point, I encourage you to pause the video and go over what you had written down to check your work. And when you're ready, let's go ahead and simplify together. So 10 over 2 simplifies as 5, so we get 5x squared plus 6 over negative 2 gives us negative 3x to the negative 2. And I have 3 over negative 3, so those 3's cancel. And the negatives cancel out here. So I get a plus x to the negative 3 plus c. And how would we check our work? Well, we need to take the derivative of that antiderivative we just found and check, does the derivative of that function we just found match up with this function in the integral? All right, so now let's take a look at our final example here. So now we have an integral of, again, a difference, but with 2 terms. And it might look really scary because we have all these square roots and cubed roots and fourth roots going on. But keep in mind that a cube root is the same thing as having a fractional exponent. So there's nothing new here other than our exponents are now fractions. So as a first step, let's rewrite this function in the integral with fractional exponents. This is going to be equal to the integral of 16 over 3 x to the 1/3 minus 15 over 4 x to the 1/4 dx. So now hopefully it looks a little less scary, and we see that the form of our function here in the integral is just like we've seen before, our x with a power. So to find the antiderivative of each term, we have our constant 16 over 3. Now my antiderivative will be x with a 1/3 plus 1 over 1/3 plus 1. Recall I just add 1 to the exponent and then divide by the exponent plus 1. If I had 1/3 in the exponent, divide by 1/3 plus 1. I'm going to subtract 15 over 4 times x to the 1/4 plus 1 over 1/4 plus 1. And don't forget, I need to add the plus c. Okay, so now we can clean this up a little bit. And I encourage you to pause the video at this point and try to clean up this antiderivative on your own first, and then we'll check answers. All right, so when we clean things up, we can add the exponents that we have here to find just one fraction for the exponent. And then also add up those denominators to see if we can cancel some things out. So first we have 16 over 3, x to the 4/3 now, over 4/3, minus 15 over 4, x to the 5/4, over 5 over 4, plus c. So now I can further cancel. So notice that if we have a fraction on the denominator, that's the same thing as multiplying by the reciprocal of that fraction. So we can go another step further and write this as 16 over 3, x to the 4/3 times 3 over 4, minus 15 over 4, x to the 5/4 times 4 over 5 plus c. So again, notice how the fraction on the denominator, we're dividing by that fraction. It's the same thing as multiplying by the reciprocal of that fraction. All right, so we can further clean this up here. Notice that in the first term, these 3's cancel. And then 16 over 4 cancels to give us just 4 in that numerator. So this becomes 4x to the 4/3. And this next term, and I'm just multiplying all the numbers here, so I could rearrange my multiplication in order to see that cancellation happen. But we see that 4's cancel numerator denominator, 15 in numerator, and 5 in denominator cancels to just be a 3 in that numerator. So here we're getting minus 3x to the 5/4 plus c. So we can check if there's any simplification that can happen. We could write these exponents as radicals once more. So if we wanted to do that, well, then we'd have 4 times x to the 4th cubed root. I always remember which is on top and which is the outside by recalling one thing is that since we're looking at thirds here, we're taking that the root should be in thirds, so it's cubed root. Another thing is to remember that the numerator always stays with that term it's on. So the top dog stays in the doghouse and the bottom one goes outside. It's another mnemonic that can help you with remembering what to do with that exponent. But so then we have 3x to the 5th, numerator stays with x, top dog stays inside, and the bottom goes outside because we're looking at fourths. So we look at 4th root plus c. So at this point, there is nothing more we can do. So our antiderivative will be this function. And again, I encourage you to check that this is in fact the case by taking the derivative of our function. When you do that, you can ask, does that derivative match our original function inside the integral? And if it does, then you know that you will in fact have that correct antiderivative. All right, great work, everyone. Thanks for watching.